So in this video, what I would like you to do is to calculate each of these 6 integrals one after the other. So this is sine of 2x multiplied by the sine of 6x integrated with respect to x, sine to the power of 4 of 2 theta integrated with respect to theta, tan cubed of theta integrated with respect to theta, cosine to the 5th of 2 phi integrated with respect to phi, p times the arctangent of p integrated with respect to p, and finally sine cubed of theta multiplied by cos squared theta, all integrated with respect to theta. And what I would like you to do is on a piece of paper write the integrals down, calculate them, and then afterwards you can scroll rapidly through the video to check if you've got them right or not, and if you have got any problems, the answers are given in detail. So with that, I think you should pause, write them down, and look at the integrals. So on this slide, what I've done is just to write down the answers for all of the integrals. And if you agree with all of these answers, then there's no need for you to watch the rest of the video. You should, of course, not be immediately concerned if your answer doesn't agree. For example, I could imagine that somebody here might have minus the logarithm of the secant of theta, but because the secant of theta is 1 over cos, that is exactly equivalent to plus the logarithm of the cosine of theta. And if you look at, say, the results that Wolfram Alpha or equivalent software give, you might find that you get quite different looking answers, but they are indeed equivalent, up to, of course, integration constants. So any video or any answer that you disagree with, you can just scroll forwards, and see if you agree with the answer or understand the answer. Okay, so with that, I'll stop. So I want to first calculate the integral sine of 2x multiplied by the sine of 6x, all integrated with respect to x. So we see here a product of two sine functions with different arguments, and this should help us think about the following formula. So let's recall the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. And this factor here, or this term here, is equivalent to this with an appropriate choice of a and b. We then use the even property of the cosine function and the odd property of the sine function to realize that from this equation here we can write that the cosine of a minus b, so this is a plus minus b, is the cosine of a times the cosine of minus b, which is the cosine of b, minus the sine of a times the sine of minus b, and the sine function is odd, so we can write that as sine of b, take out a minus sign, and that means we add another minus sign here, and minus times minus becomes plus. We now have two equations, we add them together, and we would see that the sine terms cancel, but if we take this one and we subtract this from it, the cosines will cancel, and we will be given twice this term here. So what this shows is that 2 sine A sine B is the cosine of A minus B minus the cosine of A plus B. And this is the formula that we now want to use, dividing both sides by 2 of course in a moment to get rid of this factor, but this is the formula we want to use to substitute into here with an appropriate choice of A and B. Now this is actually symmetric if you swap A and B around, because it's just swapping the order of the sine functions. So in many ways it would be very sensible to say that A is going to be 6x and b is going to be 2x, because then you get the cosine of 4x here, and here you would get the cosine of 2x plus 6x, which is 8x. But what I'm going to do is just not to do that, do it the other way, and see how things can still be made a little bit easier. So what I want to do is to say let a equal 2x, b is equal to 6x, so a minus b is minus 4x, and a plus b is 8x. So therefore our integral, the sine of 2x times the sine of 6x integrated with respect to x, is going to be the integral of 1/2, open brackets, cosine of minus 4x minus the cosine of 8x, all integrated with respect to x. And what I want to point out here is that although we could integrate this directly, it is much easier if we just immediately say that the cosine is even, so the cosine of minus 4x is equal to the cosine of 4x. If we had a sine function here, then the sine function would be odd, and so for example the sine of minus 4x can be written as minus times the sine of 4x. And I think using those properties will make integration and differentiation generally easier. So in our particular case, what we have is 1/2 is a common factor that multiplies everything, so I'll take it outside. We have a difference, or the integral of a difference of terms, so I can write that as a difference of integrals. We have the cosine of 4x, having used the even property, minus the cosine of 8x, close brackets. So this is going to be 1/8 times the sine of 4x, and if I differentiate this, the sine becomes a cosine, and I'm going to pull out a factor of 4 from the chain rule, and 4/8 is 1/2, so that's correct. Minus 1/16 times the sine of 8x, and that is our result for the integral. So with that, I will move on to the next integral. So the next integral we want to look at is the integral of sine to the power of 4 of 2 theta integrated with respect to theta. So what we hopefully see here is that the power of the sine function is even, and this should make us think that we can use a double angle formula. So what we want to do is to recall that the cosine of 2a is cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. These three equivalent formulations of the right hand side can all be used for various integrals, but this form here is appropriate for this integral. This integral is an even power of sines, so this is the formulation we'll use. So let me put the left hand side down here as well. The cosine of 2a is this, so this tells us that sine squared a is 1 minus the cosine of 2a, all divided by 2. So therefore, sine to the 4th of a is 1 minus the cosine of 2a over 2 all squared, which is 1/4, 1 minus 2 cos 2a plus the cosine squared of 2a, close brackets. Now, at this stage we realise that if we were to use here with 2 theta here, we would have 1, which is easy to integrate. The cosine of this with 2 times 2a, 2 times 2 theta, which is 4 theta, which would be easy to integrate. And this term, which involves the cosine squared of 2 times 2 theta, 4 theta. The cosine squared can be integrated by coming back to our formulae here and looking at this side. So let me again put in the left-hand side. The cosine of 2a is this. So what we see is that the sine to the power of 4 of a is 1/4, open brackets, 1 minus 2 cos 2a, and then we have the cosine squared, and we look back at this equation here. The cosine, 2 times the cosine squared is cos 2a plus 1, taking this over here, so the cosine squared can be written as cos of 2a plus 1 all over 2. But here we have cos squared of 2a, so here where we have a, we replace it with 2a, here where we have 2a, we replace it with 4a. So we have plus cos of 4a plus 1 all divided by 2. So if we just tidy this up a little bit, we have 1/4, we have a 1½ that we can add together, so we get 3/2 minus 2 cos 2a plus 1/2 cos 4a. So if we say that a is 2 theta, we have sine to the 4th of 2 theta is going to be 1/4 times 3/2 minus 2 times the cosine of, now a is 2 theta, so 2a is 4 theta, plus 1/2 the cosine of, a is 2 theta, so 4a is 8 theta. And now we have rewritten our integrand in a way where we can integrate this term, and this term quite straightforwardly. So this tells us overall that the integral of sine to the power of 4 of 2 theta with respect to theta is going to be 1/4 3 theta over 2 minus, and now we divide this next term here by 4, so we have minus 1/2 sine of 4 theta, and then we have plus 1/16 times the sine of 8 theta. And it's good practice just to differentiate these results in your head to make sure that yes, we do get back to our starting line and that we have calculated the integral correctly. And with that, we can move on to the next integral. We could of course also, just to tidy things up a little bit, either bring the quarter into here, here and here, or take out a common factor of 1/2 from here, here and here. But I'll move on to the next integral now. So this integral is the integral of the tangent cubed of theta with respect to theta. We look at it, can't immediately do it, and think of an identity which should be the tip of our tongue whenever we're trying to integrate powers of tangents. And so let's recall the identity that sec squared theta is 1 plus tan squared theta, or tan squared theta plus 1. and this is an extremely useful identity for integrals involving powers of secants or powers of tangents. So in particular what I'm going to do is to break this up, the tangent cubed, as tangent times tangent squared, so that I can use this identity. So the integral of tangent cubed of theta with respect to theta is the integral of tangent of theta times tangent squared, but tangent squared I can write as sec squared theta minus 1 integrated with respect to theta. So this gives us two integrals now. It's the integral of the tangent of theta times sec squared theta with respect to theta minus the integral of the tangent of theta with respect to theta. So we look at this integral here, and we remember that sec squared is obtained by differentiating the tangent of theta. So we have the tangent times its derivative. And this means that this is an integral that we can just do. We can identify the answer. You can also use a substitution, but I think this is one that you should aim to just recognize. So this is going to be tangent squared theta, because if I differentiate it, I'm going to bring down a factor of 2, and I don't like that, so let's immediately put a factor of a half down, which will cancel it. I will then be left with tangent to the power of 1, which I like, multiplied though by the derivative of tangent, and that is sec squared, and that's exactly that. So this is the result of that integral, and we know it because if we differentiate it, it works. And then we have minus the integral of the tangent function, and the integral of the tangent is one that we should know, and it is the logarithm of the secant function. And because we have a minus sign here in front, I would tend to take the minus sign into here and use this as therefore as plus the log of 1 over sec, and 1 over sec is of course cosine. So this is a half tangent squared of theta plus the logarithm of the cosine of theta, plus, if you wish, an integration constant, which we should always understand as being there. So this is our result for the integral, and with that we can move on to the next slide. So in this slide I want to calculate the integral cos to the power of 5 of 2 phi with respect to phi. And what we have to notice here, the important pattern, is that the cosine here is raised to the power of 5, and 5 is odd. So because of this, we can write this as the integral of the cosine of 2 phi times cosine to the power of 4 of 2 phi with respect to phi. So what we're able to do is to pull out one of these factors, and we are left with an even number of powers. So this means that we can write it as the integral of the cosine of 2 phi times 1 minus sine squared of 2 phi, all in brackets, squared with respect to phi. So I've written cosine to the power of 4 as 1 minus sine squared, all squared. So now we expand the brackets and we obtain the integral of the cosine of 2 phi times 1 minus 2 sine squared of 2 phi plus sine to the 4th of 2 phi, close brackets, all integrated with respect to phi. So now we have got three integrals: the integral of cosine of 2 phi, which is standard, the integral of the cosine times sine squared, both of 2 phi, and that is not a difficult integral, and the cosine of 2 phi times sine to the power of 4 of 2 phi, and that is essentially identical to the first one, but with a different power. So let's calculate all of these in turn. So the integral of the cosine to the power of 5 of 2 phi with respect to phi is the integral of the cosine of 2 phi, and that is 1/2 sine of 2 phi. If I differentiate it, I bring the 2 out, that cancels the half, and sine becomes cosine, and that's exactly that term here. And then we are going to have sine to the power of 3 of 2 phi. Now, if I differentiate that, that's 1 power higher than we had here. I'm going to bring a 3 down, and I'll have 3 times sine squared. And then when I differentiate 2 phi using the chain rule, I get a factor of 2. So I'm going to have 3 times 2. And I want the minus sign, and I would like the 2, but I don't want the 3. So I see that I have got to put a factor of 1 over 3 here. And with that, if I differentiate it, I indeed obtain this times that. And in a very similar way, for the final term, we have plus, and then it's going to be sine to the power of 5 of 2 phi. And if I differentiate that, I will pull out a factor of 5 and a factor of 2 when I differentiate that. So I'm going to get 10. I don't want the 10, so I put 1 over 10. And I know that that is correct now, because if I differentiate it, I obtain what I originally had. So this is our result for this integral. It's interesting perhaps here to use a facility such as Wolfram alpha and to ask it to calculate the integral, and it will give you the integral expressed in a completely different way, and or at least it did when I tried it, as sines of 2 phi, 6 phi and 10 phi with various coefficients. And you could try to go through the effort of trying to show that that's equivalent to the result that we've obtained here. But I'm going to stop here and move on to the next integral. So our penultimate integral is the integral of p times the arctangent of p integrated with respect to p. I look at this and I cannot easily tell what the answer is going to be. And the thing that I know well about the arctangent is how to differentiate it, so I'm going to use integration by parts for this product, and this is a standard thing that we do when we're trying to integrate the inverse trigonometric functions. And if you were just trying to integrate the arctangent on its own, you would write it as 1 times the arctangent and still use integration by parts. So let's look now at integration by parts. So let's just recall that the integral of u v prime with respect to p is uv minus the integral. Now we differentiate the u instead, and we've integrated the v prime. So that's the integration by parts formula. We are going to say that u is the arctangent of p, because we know how to differentiate it. So u dash, the derivative of the arctangent, is 1 over 1 plus p squared. And v dash, the term that we want to integrate, is p. So the integral, I'll cross that out, the integral of v prime, v, is going to be 1/2 p squared. So therefore, the integral of p times the arctangent of p is going to be u times v, which is 1/2 p squared arctan of p, minus the integral, and now it's 1/2 p squared times 1 over 1 plus p squared, so I write that as p squared on the top over 1 plus p squared, all integrated with respect to p. Now what I have here, the integral we still need to calculate, is an improper rational function, because the highest power of p, here p squared, is in this case the same as the highest power of p on the bottom, which is also p squared. So what I want to do, if I look at this, is I think if I had p squared plus 1, this would be easy. I just have a 1. So I'm going to add a 1 here, but then of course I have to subtract it. So let's see what happens that way. So our integral is 1/2 p squared arctangent of p minus 1/2, and now I'm going to take the half out and open brackets. We have the integral of p squared plus 1 minus 1 over 1 plus p squared, integrated with respect to p. And this is 1/2 p squared arctan of p minus 1/2 brackets. Now, p squared plus 1 over 1 plus p squared is 1. So it's the integral of 1 minus, and then we have 1 over 1 plus p squared. So this is 1 over 1 plus p squared, all integrated with respect to p. So we have a difference of two integrals here. We have the integral of 1, and that's just p, minus the integral of 1 over 1 plus p squared, and that is the arctangent of p, because we know what the derivative of arctangent is. We have that here. So if we integrate that, we get back to the arctangent. So we have, therefore, 1/2 p squared arctangent of p minus 1/2 p, minus minus becomes plus 1/2, and as we just said, the second integral here is the arctangent of p. So therefore, the integral of p times the arctangent of p with respect to p is, there is a common factor of 1/2, and we have p squared plus 1 times the arctangent of p minus p on its own. And that is our result. For the integral, we can add an integration constant, and it's a good exercise, of course, we should always be doing this. It's a good exercise to differentiate our result and see that we obtain the original integrand. And with that, I'll move on to the next integral on the next slide. So in this integral, we have the sine cubed of theta multiplied by the cosine squared of theta. They have the same argument, and we notice that one of the powers is odd. And if one of the powers is odd, what we have to do is to pull out a factor of that function to leave us with an even power, and then to try to rearrange in a way where we can just write down what the integrals are by inspection. So we note sine cubed of theta is an odd power, and proceed as follows. So we write sine of theta times sine squared of theta times cosine squared of theta, integrated with respect to theta. The sine function here on its own to the power 1 is the derivative of cosine up to a minus sign. So I want to write everything here now, which is purely even powers, in terms of powers of the cosine function. So this is done as follows. We have the sine of theta. The sine squared becomes 1 minus cos squared. And cosine squared of theta is already in the form we want, and then this is integrated with respect to theta. I'll just squeeze it in here. So what we have is the integral of sine of theta times, and then it's cos squared theta from when the 1 is multiplied by the cos squared, minus, and then we have cos squared times cos squared, so that's cosine to the power of 4 of theta integrated with respect to theta. And now we have two different integrals, and we see, just to return to our result, that the integral of sine cubed theta cos squared theta respect to theta is equal to the integral of sine theta cos squared theta integrated with respect to theta minus the integral of sine theta cos to the 4th of theta integrated with respect to theta. So, we look at the first integral. This is the cosine squared multiplied by its derivative up to a sine. So if I increase the power by 1, I would have cos cubed theta. If I differentiate cos cubed theta, I bring a 3 down, I reduce the power to cos squared, and I multiply by the derivative of cosine, which is minus sine. I don't like the 3 and I don't like the minus sign, but it's easy to fix that. I can write this as minus 1/3 cos cubed theta. Pause and check. If I now differentiate this, I bring the 3 down, that cancels that. I've got a factor of cos squared, which is this, and I multiply by the derivative of the thing that was cubed. That was a cosine, and I get minus sine. Minus times minus is plus, and I'm left with a sine, and that's what I would want here. So this is the result for that integral. And in a similar way, here I'm going to get plus 1/5 cosine to the power of 5 of theta plus some integration constant. And yes, if I differentiate that, I pull down the 5, I get cosine to the 4th, and I have a factor of minus sine of theta multiplying it, and that gives me the minus sign here and that. So this is the correct answer for this integral. So we have that the integral of sine cubed theta cos squared theta with respect to theta can be written in this way. And with that, I will end this video.